Up next, we have Parikshit Pareek from IIT Roorkee.
So hi. So this talk is not about LLMs, right? And I am between you guys and tea, I guess. So good luck with the tea. My name is Parikshit. This talk is about physics-informed ML. This talk is about trying to build something for just for you maybe, and not worrying about if I'm building for everybody a sledgehammer, right? So bear with me. I will be here for the tea. I know there will be a lot of questions left because this will be slightly more technical than what we are seeing till now. Heads up is that I'm a faculty, so you can imagine a few math equations and graphs going here and there, right? Okay. So for me as a person who works for use ML or built ML for science, the ML time equation looks like this, right? So I cannot imagine having internet level data for my problem. It's very important to understand we don't have internet level data for any problem other than the language. So I will consider the time I take to get the data. I'll also consider time it takes to train the model. Why? Because there will be recurring situations where I need to retrain my model. So I cannot take like month to train a model, the problem which requires, let's say, next 15 minutes I need to solve, while with training, predictions and everything. And of course, time to predict, which is, I agree, which is marginal, but just for the completeness, I'm mentioning it, right? And we have a situation where all our models can be defined like this. They are trained for a data, you got the data, you are assuming that is coming from the same distribution which your testing data will be coming, then only learning is feasible, and you have a model weight. The challenge is what happens when data changes. Data keep on changing, right? One option is you built an LLM which encompasses almost all the possible cases you can imagine. But think for a minute, how many of us thinks that I can put a supercomputer to every problem? Yesterday, NVIDIA was showing a one with 72 GPUs. Can we throw that GPU to every problem? Is it wise to throw that GPU at every problem we have? At least I don't like to believe so. We can argue later on the tea, right? So, quick heads up on the method we are attacking. The method is called Gaussian process. It existed before deep learning hits its, 2012 of deep learning hitting. The idea is very simple. The more you know about something, the better you get at it. It's a Bayesian prediction. You get the data, you update your beliefs. You get more data, you update more beliefs. The shaded region at the red points where you have the data is 0 because you know about them with certainty. The model is notably good in telling you how confident it is about a particular prediction. So it's not just telling you, okay, this is the next word I should get. It's also telling you what is the probability that this is the correct answer, okay? And on the right hand side, you see a depiction of the same thing. And this presentation is all about getting these blue color distributions without going through the costly optimization and getting the parameters of this model. Okay, if you have not heard of Gaussian process, that is fine. Just think like this. You have a machine learning model, your favorite model, which you train to get the weights and parameters of, right? What if I give you another model which gives you the weights instantly? And you deploy your favorite model to your problem and not worry about training it, because training is becoming just a forward pass. Training your favorite model is reduced to a forward pass by another meta model. That's it. This is the whole thing I'm going to talk about. And the whole presentation is about single point, right? That is, you always need to ask the simplest question possible to find the answer. At the end of the talk, you will realize that it was just a simple trick which solved the purpose, right? Okay. Now, what's the goal? I said that you want to predict the model's weights. How you predict model weight in this case is doing Bayesian inference. It's same as stochastic brother of backpropagation for those who have not worked on Bayesian models, okay? Why? Of course, it's slow, right? Everything when you make it stochastic is slow. And as I said that you want to do it repeatedly again and again, the challenge becomes, pronounced as many times as you need to do it, okay? So we want to learn the approximate posterior predicted distribution, the fancy name of that blue color graph which I just showed you. I want to know how my prediction will be distributed. That's it. I want to know that, right? That's the fancy name. So what I want when I'm imagine you have trained the model and everything is done. You have a model with you, right? What do you want? I want, give me a new data on which I want to make prediction. I will give you the parameters of your favorite model to do the prediction, right? Or I will give you the prediction which is matching with your true model. You can directly use it, right? But there is a model in between. The whole thing is built to do Bayesian inference, not for any random model. It's really, really important to understand. That's why I'm saying this talk is about making something you want to make for your particular problem, not a general case tool, okay? Now, okay, so what is PFN? I'm sure not many of much have heard about PFN, which is called prior data fitted networks. It's a very simple thing. I collect infinite orly large or significantly large millions of billions of such things. How I collect? I just generate them. They are just generated between some 0 and 1 and -2 and 2, right? And I say that I don't know one data point. X is a holdout sample. I don't know that, right? This is all synthetic data. So it's cheap. That's why I said the time to prepare data, I want to be cheap if I want to deploy it in science, right? Very simple. I just tell it, this is just one way, negative log likelihood. You can make it another one. I just tell the model, okay, learn to predict this X given the blue ones. What I'm saying, its fancy name is few shot learning, but what I'm saying learn to know X if I have given you the blue guys. That's it, right? Then when I go and ask it finally what for my query, I give it the blue guys. I ask what is the value at the red dot. It should give me the distribution, not a point, a distribution. Again, this distribution is called predictive posterior distribution, right? Now, if you notice, I did not define the problem. I did not tell you where my data lies. Essentially, I am building a regression foundation model. Anything, if I can scale it to this region, I can just throw at it, and if it is trained correctly, it should be giving me this, right? So that is the whole idea. You collect the synthetic data, you train your machine which does the regression for you on synthetic data. Now you want to do regression on any data set which machine has not seen. You just need to bring it to the level of machine normalization and just throw it, right? So it's a foundation model to do regression of a particular task type, okay? So this is the fundamental paper which came out in 2022, which said transformers can do Bayesian inference. So this is what I just showed. You have this data set, collect the K data sets out of the distribution, train on K. During prediction, you give the D context. You need to give it data. It's not non-data prediction, but you don't need to retrain your original model. It just starts to give you the Q theta. It just gives you the predictive distribution. It does the regression for you, gives you the weight in a single forward pass for again and again and again and again a new point. That's the important point, okay? So far so good, but we ask 1 plus 2 simple question. It's extremely simple. Everybody in our area asks this, right? Will it scale? Right, that's the first question. Will it scale? Will it scale for 50-dimensional regression, not classification? Because in regression, when you go for larger dimension, the distances collapse. And then you have a large dimensionality curse problem, much more pronounced, right? Turns out, no. None of these scale. Okay? Then we ask the associated question. That is, why everyone, so this was built on transformer, there was an attention, and everyone was encoding X plus Y together. So what they were doing is, I'll show you a diagram. They were saying X and Y, they add them, then they do all the processing, right? Why? There was no motivation. Turns out this is how language models were built. And people took it from language models, and nobody dared to ask in last 3 years in this community that, hey, why are we doing this, right? And how does this affect localization? So anybody who has done a even simple regression or trying to predict, interpolate, you know that the points which are nearby should affect my prediction more, rather than the point which are global, unless I have a global pattern like periodicity, right? But how does it do? Because if you add all y's in all x, you are actually losing that localization. You can imagine I'm putting up a noise in the model, because in language, this is how models were trained, right? And the second question we asked, why in last 3 years, everybody is building on transformers? Is it just because transformers is a new thing in the town, new kid in the town, or there is something more to it? Again, a very simple, first question should come to your mind, right? Can I make it with CNN, LSTM, or anything? Forget about arguing that, oh, LSTM is faster and all. We'll see that later. But first fundamental as a science question is, we should not leave these questions in a hurry to deploy something and something, because we might have benefits to gain there. CNNs will be much cheaper, lower in size and all, right? Okay. So this is the attention which I was talking about, right? So they add these two, the simple attention, right? And then just calculate these things. Everything all W's are parameterizable. Phi is also a trained MLP and all, right? And then they calculate attention. Our simple trick is, hey, why not just decouple it? Let the value pass through value, let the output pass through the value key, and let the input only play in carry and key, right? Value calculated with output, very simple, single line idea, nothing is fancy, right? And then Q and K is calculated when using only input. This enforces this inside weights of this value to be just localized on inputs, right? Those who know Gaussian process can relate that this is nothing but weights on a basis. This is a basis, kernel basis, and you have weights, right? So this is just an inspiration taken from there. Simple idea, separate it. We looked the literature, nobody has done it, right? I'm still not sure why. But keeping input and output separate, okay? Now, then, of course, we did what all academicians do. We tried to prove it. That can we prove some kind of nice property for this? And turns out, yes, we can prove that there is an exponential decay, proportional exponential decay, when based on the distance between the query, between the target. Okay, I want to know what is my y at x star. That is x star. And xi is something which I am giving as blue dot. X star is a red dot where I want to know what is the output. Xi is one of the blue dots, and you have multiple such blue dots. So the weight is proportional to exponential decay, which is like RBF kernel. So, right? But does it hold? Theories doesn't hold in practice, generally. A lot of time in machine learning and deep learning. So does it hold? Yes, it does. This is the vanilla prediction people were doing. When you go from distance, these are the weights how look like. And look, I mean, at least my eye says that this is like exponential decay, right? And then this theory, this holds really nicely, right? So one thing we achieved, we said why we are doing x plus y, don't do x plus y. When you don't do x plus y, you can achieve localization. So now my regression should look like regression, not a global parameter dependency like a language. What, again, for LLM, people who are more familiar with LLM, I am not contextualizing my prediction on all the paragraph. I'm kind of contextualizing it around the words, right? We went to all the paragraph because we wanted that feature in language, right? We don't want that feature everywhere. So let's not impose that feature everywhere blindly, okay? What about scale, performance, right? So you see that in lower dimensional, CNN, transformer, both with vanilla attention VAs are as good as our decoupled value attention, right? It's DVA is nothing but decoupled value attention, right? So, but when I go for larger dimension, 5-dimensional, it's just not there. Like, in fact, 10D, we realize that it just doesn't train even. Look at this corner graph, the bottom right corner, right? This is 10-dimensional. Another important thing here is, yeah, you can make it with CNN. Voila, nobody thought of it, right? There is a good amount of literature if you go on prior data fitted networks in this area, but all exclusively before this work is on transformer. Even the theoretical analysis uses transformer. Everything is on transformers, right? And so this establishes two things. You can do CNN, and you can also say that, okay, decoupling works, just enforces localization. We said, what if I don't use softmax attention and I use linear attention? Okay, it's faster, right? So decoupling should help there also, right? Turns out, yes, best is softmax attention in terms of performance, but slower to train, as we know it, right? Then comes the linear decoupled attention, then comes the softmax vanilla attention, and then comes the linear vanilla attention, right? You can see that. So now the point is, don't worry about these large dimensions. This just doesn't train. We tried everything. We tried Optuna, hyperparameter tuning, 1000, almost went to our GPUs for days, but nothing. It doesn't just train, right? Okay, CNN is the only guy which beats transformer? No. LSTM, RNN, you just name it. Like almost any network you can make your own PFN. Now why it's important to try on different networks? Because your problem might have some feature which are more supportive for one particular type of network. By showing this, we have built a capacity that you can inject more and more about your own problem, okay? So, we have achieved both objectives, right? You can do localization, you can scale, 3 actually. You scale, localization, as well as the CNN, RNN, LSTMs, right? But I started with the talk that this is physics talk, right? So I'm a power engineer. I'm not an ML guy. I'm trained power engineer. I wanted to do power flow, a problem where you want to know what is the state of a network, right? On a grid, you have generators and load, our transmission grid, right? So we tried on a problem which has 64-dimensional input, real and reactive powers, and a lot of jargon, but you can assume it's 64-dimensional regression, okay? Then we saw, of course, the exact Gaussian process will beat everything because you are doing an approximation. That's fine. But we are able to make it engineering level approximation already while it's 80 times faster, even just for single trial. Multiply this with the factor how many times you want to try these models to be trained, okay? You increase the context, you get the better performance. Means more blue dots, it should improve its performance, right? That's what is expected. If you give it more information, it should get better. That's what the core of Bayesian learning is. Give me more data, I update my beliefs, unlike humans, right? What happens in 100 dimension, right? Is it 100 dimensional stable training? Yeah, 100 dimension is a stable training, right? So you are looking at a 100 dimensional regression foundation model. So these are just simple summaries that, yeah, decoupling is better, you reduce bias, your attention is better, more important than the backbone, scaling to 64-dimensional. The big question is again, which I already alluded to, is that can we make a foundation model for regression? Now it will be super powerful for science. You do regression every time, right? All the time, right? So can we make it? So that's the idea we are jumping. Last slide. So you know the best part of this? The two people who ran this are third-year undergrads. I'm a new professor, new assistant professor, just spent my 1 year, and I don't have a grad student till recently, right? So all this work was done by two undergrad kids. These are their pictures. You can get the full preprint on our lab website, but it's the best part. But like two third-year undergrads ran this. We went to a top ML conference. Some fiasco is going on there. Those who know, we are hoping for this, but preprint is there with proofs and all the results, and yeah. One good thing with working with undergrads is they don't care if it is accepted. If you don't care, right? Their graduation doesn't depend on it. So it's a good bit if you work with undergrads, just that it takes a different kind of, pain to work. And there should be one more. Okay, there should be one more thing coming up here, which is funding support by ANRF, Early Career, and IIT Roorkee. I'm not sure if they are dispensable, but they became one. Yeah, thanks. Open for questions.
Okay. Thank you, Professor Pareek. We'll take two quick questions.
I have one question. So basically, when we are creating foundation model for regression, so what should our training data should look like? Suppose I am doing regression by giving training data of all polynomials or all say sinusoidal function. So when I am doing inference, so are they kind of linear combination of all these things?
So the answer is that no. So when you want to build a regression foundation model, you want to give all type of synthetic data which you believe that you will be getting. So to do that, what we did, we generated that from different types of kernel. So Gaussian kernels can approximate a lot of different kind of things like polynomial kernel, RBF kernel, Martian kernel and all. And that's how we generated a lot of synthetic data. What we are relying on is the power of a good normalization. No matter where your data is, you can scale it down, bring it to the level where model understands that, and then just pass it. It's like embedding. Simple normalization we are treating as an embedding.
So suppose if there is some high gradients in my regression, like function increases and suddenly dips
non-smooth,
down.
completely non-smooth. If you want to build a completely non-smooth regression, then build a model for non-smoothness. So the framework will allow it. We didn't do that.
Okay.
Right? As you saw, we worked for smooth because the function I was interested predicting power flow is a smooth function.
Okay. Right. Thank you, sir.
One more question.
Either I explained it everything well or nothing at all.
Okay.
There are only two cases. Thank you.
We can continue our discussions during the coffee break. We'll now break for coffee.